Alright, this example is on Laplace and Poisson equations. Now suppose we have two infinite parallel plates existing in free space and are separated by a distance of 1 centimeter with a potential difference of 9 volts across the plates. So we're going to find the first part A, the potential difference everywhere between the plates, and then the electric field everywhere between the plates. So let's start with, of course, part A. So we're looking for the potential difference or the voltage. Now, I've already drawn the figure here, all right, for the sake of time. And you need to be able to draw such a picture based on the problem description. So if you're not comfortable with that, maybe practice. But I've shown my infinite plates here, and I've aligned them to be in the YZ or along the x-axis anyway. So they're in the x-axis, and one of the planes is at the x equals 0, or is the x equals 0 plane, and the other plane is the x equals 1 plane. And I've chosen that so we just work in the x direction. I mean, you could do this in the y direction or the z direction, but you want to align them in one of those dimensions to make your life more simple. And then I've chosen x equals 0 because 0 is a nice number, and I've chosen to give that 9 volts, and then x equals 1, so this is 1 centimeter over here, and that one is grounded. And so that way the electric field, which goes from positive to negative, points in the positive x direction. So we're working with positive numbers here. All right, and remember, I just want to point out infinite plates seems kind of silly, but infinite, what that really means is that the dimensions of the plates are larger than all the other dimensions that you need to consider. So here we're considering this 1 centimeter. So all this really means is that the plates themselves are much larger in dimension than 1 centimeter. Okay, and so we're going to calculate the potential difference everywhere, and so we're going from 9 volts to 0 volts. So that's the boundary condition. So how does it change from 9 volts to 0 volts? That's what we're going to try to answer first. So we need Laplace's equation, because we're in free space and there are no charges in between our plates. So we're told free space, and we're not told anything about charges there, so we can assume that we need Laplace's equation here. Now also, there is no variation in the y or z direction. Imagine these plates are infinite and you're between the plates and you walk down the y-axis, or you walk in the y direction. Everything would look the same to you because the plates are infinite. You're not approaching, the ends of the plates or anything like that. So everything remains constant. There's no variation there in the y direction. And same thing with the z. If you were to, take a hot air balloon or something or whatever and rise, or a helicopter and rise in the z direction, then everything would look the same to you there as well. And so the only variation we have is from going from 9 to 0 in the x direction. So that is all to say that Laplace's equation reduces to this. Okay, so now we integrate once, so we have the second derivative of v is 0, so that must mean that the first derivative of v is a constant. So I'm going to call it constant c1, right? Because then you take the derivative again, you get 0. Then when you integrate twice, right? Well, this is saying that the derivative is a constant, so when you integrate twice, then you get this. When you integrate a constant, you just tack on the x, and then you get another constant of integration. And you can check yourself by taking the derivative of this thing twice and see if you get back 0, and you do. So now we need to find those constants, and so we plug in our boundary conditions. We know that at x equals 0, we have a potential of 9 volts. So when I plug in x equals 0, notice the c1 will cancel. So x of 0 should be x at 0 should be 9 volts, and so that is equal to C2, right? When x is 0, I just have C2. So now I've got C2, and then I plug in the other boundary condition at 1 centimeter. Okay, so I'm just going to keep in mind that this is at centimeter. V of 1 should give me 0 volts, right? And so when I plug in 1 here, I've got C1 plus C2, and C2 is 9. So that must mean that C1 is minus 9 volts. And so then I plug 9 in for C2 here, and I plug minus 9 in for C1 there, and I find that now my specified solution to Laplace equation is 9 times, if I factor out the 9, 1 minus x volts, right? And I'm just going to point out here that, again, x is in centimeters. Okay, and so this is the solution to the Laplace equation, and sometimes you'll see the profiles sketched. So remember, we wanted to know, well, how does the voltage change from 9 volts to 0 volts? So that's given by this equation, and we can plot that equation. That's helpful to see. So if I plug in 0, of course, I have 9 volts in my equation, right? And if I plug in 1 centimeter, right, 1 centimeter, of course, I have 0 volts. And this is a line, right, with a slope of -9. So it goes like this. And so this is the profile of the voltage. That's how the voltage changes. It changes linearly in this case. Okay, so now we're going to go to part B, and we're going to remember that the voltage was 9, right? 9 volts. Or I guess we're told 9 volts in the problem. Actually, I'm going to keep the thing in the box. Okay, so here's part B now. We want the electric field. So how are the electric field and the voltage related? Well, the electric voltage is the negative gradient of the electric field is the negative gradient of the voltage. So this means that E is equal to, so I take the gradient here, but all the gradient is, since I have one variable, x, is the derivative with respect to x. So the derivative of v here with respect to x is just -9, and so I have a negative here, and so this just makes 9. And since I took the derivative in the x direction, this is 9ax. Remember the del operator, how the del operator works, and so I get this electric field as 9ax volts per centimeter. Remember that x was in centimeters, and so then if I want to convert that, then I see that our electric field is 900 in the x direction volts per meter, and that is the answer.